In this video, we're going to talk about three different ways of describing reactions that occur in solution. The first way we can describe a reaction that's happening in a solution is with a molecular equation. This is the kind that we're the most familiar with right now. These use complete formula for all the reactants and products. They don't show the presence of any ions, even though we know that electrolytes should show the presence of ions when they're in solution. And this is really useful for planning and running experiments because you know exactly which complete substances you have to go get from your supply cabinet or wherever the supplies are. So for example, let's say we were going to run this reaction. Aqueous lead-2 nitrate reacts with aqueous potassium iodide to produce aqueous potassium nitrate and solid lead-2 iodide. The molecular equation would look like this. You'd write the formula, the complete formula for lead-2 nitrate. So that'd be Pb with a 2 plus, NO3 is 1 minus, so when you charge swap you'd have a 2 there. And this is aqueous, so we put a little AQ there. Reacts with, so the other reactant is aqueous potassium iodide. So potassium is 1 plus, iodide is 1 minus, AQ. To produce, here are our products. Aqueous potassium nitrate, so potassium is 1 plus, nitrate's 1 minus, so KNO3, aqueous, and solid lead-2 iodide. So PbI2, and that doesn't dissolve in water, so it's a solid. Try this one. Write the molecular equation for the reaction between aqueous silver nitrate reacting with aqueous sodium chloride. Stop the video and write this out, and I'll bring you the answer in a little bit. Okay, aqueous silver nitrate would be AgNO3. It's 1 plus 1 minus, so there'd be an AQ. And aqueous sodium chloride, NaCl, AQ, dissolves in water. Our products are going to be, because this is a double replacement, the inside two species and the outside two species together. So sodium would go together with nitrate, and that would be soluble, because group 1 salts are soluble, so are nitrate salts. And then silver would go together with chlorine. Silver chloride is insoluble because lower halides are not soluble with silver, mercury 1, or lead 2. So that's the molecular equation. Let's try this one. Write the molecular equation for aqueous hydrochloric acid reacting with aqueous lithium hydroxide. Hydrochloric acid is HCl, aqueous, and lithium hydroxide. Lithium is 1 plus, hydroxide is 1 minus, so LiOH, aqueous. When these react, this is an acid-base reaction. The products are going to be water, which is, we don't write aqueous, it's actually liquid, but that's usually implied for water. And then lithium together with chlorine. Lithium chloride would be soluble, so you'd write LiCl, aqueous. One more. The molecular equation for aqueous hydrofluoric acid reacting with aqueous calcium hydroxide. And CaF2 is insoluble, so that might help you predict the products. Hydrofluoric acid, HF, aqueous, reacting with aqueous calcium hydroxide. Calcium's 2 plus, hydroxide's 1 minus, so there's the correct formula. Aqueous, and they're going to produce calcium fluoride will be one product. Calcium's 2 plus, fluoride's 1 minus, so CaF2. And this is insoluble, so we know that's going to be a solid. And then the other product would have to be hydrogen with hydroxide. Well, that's just water, HOH or H2O, which is implied to be a liquid. Now, this equation isn't balanced right now, so I'd need a 2 in front of the HF to balance the fluoride, and I need a 2 then in front of H2O to balance the hydroxide and the water. That's HOH, 2 of each. The next kind of equation that we're going to use to represent reactions that happen in solution is ionic equations. In ionic equations, all the electrolytes are shown as ions. So what that means is you're going to have to split up any soluble salts, and you're going to have to split up strong acids because they are mostly ions in solution as well. In addition to showing the matter balancing, you also have to make sure that the charge balances, the pluses and minuses, have to balance each other out. What this is good for is it allows us to visualize what's really happening in the reaction once we split out all the ions, and we can start to see that some things really aren't participating in the reaction, they're just there. So this was the molecular equation for lead nitrate reacting with potassium iodide. Let's write out the ionic equation. Because lead nitrate is aqueous and it's a soluble salt, we would write this split up. So I'd have Pb2 plus 2 NO3 minuses. And I could put the little AQ there, but I don't really need to because it's sort of implied if I'm showing the ion split up in solution. Plus Ki. So 2 Ki's gives me potassium 1 plus and 2 iodide, both aqueous. Other side of the arrow, I have potassium nitrate. That's soluble, so I would split that up to 2 K pluses and 2 NO3 minuses. But PbI2 is a solid, and I can't split solids up because in solution they really don't split up. And so I'd have to leave that together as PbI2. So there's my ionic equation that goes along with this molecular equation. This is a molecular equation for a reaction that you did earlier. Write the ionic equation for this. Stop the video and try to work it out, and I'll give you the answer in a little bit. Well, AgNO3 is aqueous and soluble, so I would have to write Ag plus NO3 minus, splitting that up. Sodium chloride also soluble, and it's an ionic compound. I split up Na plus and Cl minus. On the other side of the arrow, I have AgCl, which is solid. I can't split that up, so it's going to be AgCl. And NaNO3 is aqueous ionic compound, so I split that up to Na plus and NO3 minus. Here's the molecular equation for the second example that you did earlier. Write the ionic equation for this, stop the video, and give it a try. Well, this QQ is really supposed to be AQ. I hope you figured that out. Hydrochloric acid is a strong acid, so when it's in solution, it mainly exists as ions. So I can write this split up as H plus Cl minus. For a weak acid, I would not be able to do that, but for a strong acid, I should. Lithium hydroxide is a soluble salt, so I split that up to Li plus and OH minus. On the other side of the arrow, I have water, H2O, which I do not split up because it's not a soluble ionic compound, and it's not a strong acid. And then lithium chloride is soluble, so I would split that up to Li pluses and Cl minuses. This is the last example that you wrote the molecular equation for. Now write the ionic equation for it. Stop the video and try it. Then start the video again when you're ready to look at the answer. HF is not one of our 6 strong acids, so I have to keep this together. So on the left-hand side, I would still have 2HF plus, well, calcium hydroxide is soluble, aqueous compound, and so Ca2 plus 2 OH minuses is how I'd show that split up as ions. On the right-hand side, I have water, which I cannot split up because it's a molecule and not a strong acid. Calcium fluoride is also not something I can split up because it's not soluble. So there's the ionic equation for this reaction. The third type of representation that we're going to use for reactions that happen in aqueous solution are called net ionic equations. These are actually the most succinct, the most powerful of all the equations because they give us the most basic information, the most important information, and leave out the things that aren't important. So they ignore what are called spectator ions. Spectator ions are species that don't actually undergo a change. What they're most useful for is generalizing about the formation of products that come from different reactions. So the solubility rules come from generalization of net ionic equations. This is an ionic equation that you've seen before. We wrote the molecular equation for this. This is the lead nitrate and potassium iodide reaction. And then we wrote the ionic equation, which we have here now. Let's figure out what the spectators are by just looking for things that don't change across the arrow. So I have 2 K pluses on the left-hand side, and I also have 2 K pluses on the right. That's a spectator. It was there, but it really didn't do anything. I have 2 nitrates on the left, and I have 2 nitrates on the right. Again, a spectator. What's left is the net ionic equation. So Pb2 plus 2I minus makes PbI2 is the net ionic equation for this reaction. Here's another ionic reaction that you've seen before for silver nitrate reacting with sodium chloride. Stop the video, find the spectators, and write the net ionic equation. Well, on the left-hand side, I see nitrate, NO3, aqueous, and I see NO3 minus aqueous on the right-hand side as well. So that's a spectator. Sodium ion appears on the left and on the right, so it's also a spectator. When I take the spectators out, I end up with this net ionic equation. Ag plus Cl minus, that should be a plus there, makes AgCl. That's the net ionic equation. This is the ionic equation for the hydrochloric acid and lithium hydroxide reaction. Stop the video, find the spectators, and write the net ionic equation. If I look on the left-hand side, I'm going to see chloride, and I also see it on the right-hand side. I will see lithium on the left side and on the right side of the arrow. So they are spectators, and I would remove them. The net ionic equation just ends up being H plus OH minus makes H2O. And this is the last example that we looked at. Here's the ionic equation. Find the spectators and write the net ionic equation. Stop the video and give this a try. Well, if you inspect this carefully, you notice that there are no spectators here. And the overall net ionic equation is the same as the ionic equation, just because of the way the solubility works here and because HF is not a strong acid. This gives you an idea of how you can represent reactions in different ways, and the net ionic equation that we just looked at most recently is probably the most powerful version of any equation that's representing a reaction happening in an aqueous solution, because it really gets to the heart of the reaction and ignores the things that are peripheral and don't matter.